Hi, I'm Rico Piccone. I will be presenting my paper with Dane Webb, my co-author today and student. New methods for metastimuli, architecture, embeddings, and neural network optimization. If you'd like to contact any of us, go ahead and drop me an email at rico@stmartin.edu. And I look forward to hearing any questions you might have about our presentation. I'll just start off with a little bit of an introduction. Dane later on will go into some of the details and our methods and results. Here we're introducing new methods for generating metastimuli, which are computer-augmented stimuli correlated with a user's own personal information management system, or PIMS, structure. This work builds from a few papers that we've published and presented previously in this conference. Figure 1 shows the metastimulus architecture. We will now animate this figure, so I won't go into detail on this slide. Okay, so we have all the same blocks that we saw in the preceding slide where we saw the metastimulus architecture displayed. But here I'm going to animate things and go into detail on how things are working. First, we have the user interacting with their PIMS, their personal information management system. A simple example is that the user might have a PIMS comprised of their notes and the tags that they have associated with those notes. So whenever the user takes a note, that would be an atom, or maybe a small part of the note would be an atom, and that atom would have tags associated with it. Now in the PIMS, we're using a very specific structure. That structure is generated from the tagged atoms. It is a hierarchy, but it's organic. It depends on the atoms that you add to the PIMS and what those tags are. This is the dialectical information architecture that we have defined in previous papers at this conference. So the PIMS has a structure in it where that atom is placed. The atom gets placed there, denoted by this dark filled in dot, and the other atoms are related to it through different category relationships. The graph that comprises the structure is then represented to the user in some way, say as a note-taking system. They would be able to interact with it in that format. So if the user wants to look at their information, of course, they're going to need to look at this structured data. So that returns down. So the user can continue to interact with their PIMS however they do. This would be an existing personal information management system structured in the way that we've described previously. So that already exists. The user is familiar with their PIMS. Remember, we're trying to build up an architecture for metastimulus. So we don't have any metastimulus happening yet. We just have the user interacting with their personal information management system. Now we have a stimulus that the user is observing. We take an atom to be something that has text associated with it, be that directly a book or a text of some sort, or an audio file with spoken language in it that could be transcribed into written text, or a video with audio associated with it that also has some sort of closed captioning or text associated with it. This text-based stimulus that the user is experiencing has a now associated with it. There is a moment in time which the user is observing this. Now that is going to be only one small part of a larger document or flow of information. However, when the user is experiencing this, what we will call atom, or this portion of information, we would like to generate metastimulus based on that portion. So of course the user experiences this directly. Simultaneously, the embedder reads in that atom, and we would like to find out where that atom belongs in their personal information management system, where it would be categorized. So we need a sort of auto categorization to occur for it to correspond in metastimuli to the PIMS of the user. So the first thing to do is to take this atom of text and embed it into some numerical form, a vector in our case, such that we can use it for an artificial neural network. We embed it word by word, as most natural language processing does. So here we see the word vectors. And then we convert that into an atom vector in some fashion. We actually have several methods for doing this. So now we have an atom vector, and we're going to take this and put it into the input of an artificial neural network. So the input of that artificial neural network we'll call X, or the embedded atom. So of course, every artificial neural network has an input or inputs and an output or outputs. We would like those outputs to be associated with the structure of the PIMS. So in order for that to happen, we need to have an interaction between the PIMS and the artificial neural network. The graph structure of the PIMS is not something that we can directly interact with the neural network in. So we have to come up with a real space vector representation of the different nodes in the personal information management system. We will take those graph structures and map them to Rn space. And that real space representation is a sort of spatial representation of the structure of their PIMS. We are associating different spatial locations in Rn with the different nodes in the personal information management system. And we've explained in previous papers why that's a potentially good thing for human learning. We take this, project it down to a lower dimension, because we can't represent a graph in its sort of native Rn dimension is very, very high dimensional. So we will compress it down to a lower dimension using principal component analysis. This will be how the PIMS artificial neural network will have trained into it what to do with these input vectors, how to associate them with these spatial locations, or these PIMS structure locations. So a trained PIMS artificial neural network will take the input X and associate it with a spatial, or RM, we have typically called it, vector Y hat. Y hat is the estimate that the artificial neural network gives for what is the spatial location for the given input atom. This vector, Y hat, can be given to an actuator. That actuator is an m-dimensional actuator, however many dimensions down to which we chose to compress this vector. So what kind of actuators? They could be haptic, they could also be visual, auditory, etc. So whichever mode or modes that we choose to actuate with for the user will be together considered metastimuli. It is going to associate for the user where in their PIMS the atom that they are experiencing, say it is a video of a lecture, which is the first type of system that we plan to study, where that belongs in their PIMS, and give them some additional redundant but also information-rich stimulus. So in this paper, we are focused on the embedder block, a lot involved there, and also the PIMS artificial neural network, how to train an artificial neural network to associate an atom that it sees with a node that is in the user's PIMS.
Similar to the metastimulus architecture, the metastimulus training is how we train the PIMS artificial neural network, which is the PIMS ANN block in the top right. In the metastimulus training, the PIMS output is a atom A and a set of categories large C. The atom A goes into the atom embedder to be embedded and outputs an embedding, or an atom embedding X. That is input into the PIMS ANN, or PIMS artificial neural network block. Simultaneously, large C, which is a set of categories, goes into the node lookup, and node lookup block outputs a node vector in the PIMS space, and that is little c. That little c then goes into the PCA projection. This is part of the PIMS filter, which I'll discuss in the next slide. And the PCA projection outputs y, which is the actual node vector, which we are training the PIMS artificial neural network to map the atom embeddings x to. The PIMS artificial neural network output or prediction y hat is compared with the actual for the atom and its set of categories. And any differences are then used to train and modify the PIMS artificial neural network weights. We need a PIMS filter because the PIMS node space dimensions n is nearly always significantly larger than the haptic dimensions m. The PIMS filter works like this. First, an atom with a location in a PIMS is identified. The atom is mapped to its node space representation via its Euclidean commute time distance. This is then projected with principal component analysis. Figure A is a demonstration of a PIMS in a dialectical architecture structure. And then figure B shows the PCA projection of that structure, where we see 3 distinct branches in both, and then there is a shared B1C1 node. Atom embeddings. The embeddings X from the embedder block in both figures 1 and 2 are atom embeddings. For our instances, and in our study that I'll kind of talk about later, we're talking about natural language, and we are using atoms in the form of paragraphs. So for our purposes, atom embeddings collate component word embeddings, i.e. words of a paragraph. And atom embeddings represent semantics of the paragraph and the word order. The PIMS ANN block in figure 1 maps atoms to their projection. It trains using the PCA projections from the PIMS filter, i.e. the PCA projection block in figure 2. And the PIMS artificial neural network weights are trained via a gradient descent algorithm. For the study, we wanted to determine whether we could use a data set that was already available to a user who had created a PIMS, and that would be the PIMS data set, to create the word embeddings. We wanted to compare this with a available data set with a large amount of data, because the concern was most PIMS or users' data sets are going to be fairly small relative to kind of the large machine learning data sets already out there. So we want to compare if specificity of a PIMS data set would make up for the small size of that data set, or would it be preferable to have just a large amount of data to create that word embedding. Another thing we wanted to study with the data and labels was how small of a output dimension we could have in the PIMS artificial neural network, where this corresponds with how simple of an haptic device we could use. Hyperparameters are a configuration that is external to the model that is not found through standard training. Some hyperparameters include the activation function of each layer, the number of hidden layers, the number of features in each layer, the gradient descent optimizer parameters, and the learning rate. These hyperparameters are optimized via Keras Tuner, which is a Python library that efficiently handles hyperparameter optimization. The Keras Tuners optimizers or tuners budget resources to find minima within the search space. These tuners include random search, Bayesian optimization, and hyperband. Metaparameters are parameters that affect the learning performance but are not hyperparameters. These include projection / output dimensions, the word embedding model / input dimensions, the keyword weighting, atom embedding methods, gradient-based optimizer, artificial neural network architecture, and tuner optimizer. For our study, we optimized our hyper and metaparameters as well as trained our artificial neural network like this. We used a genetic algorithm which forms generations of metaparameter sets. The fitness, which is the training loss of the artificial neural network of each metaparameter set model is found with the tuner during hyperparameter optimization. Best performing metaparameters are more likely to have versions of them appear in future generations. The best models from the meta and hyperparameter optimization are fully trained, then used to predict the testing dataset vector representations of their categorization. Each component is then compared, and a norm percent error is found for each prediction's actual pair. For our best results for the study, we separated them into each component or each dimension. We compared the prediction and actual, as you can see here, where the blue is prediction and orange is actual. And then in figure A, and in figure B, we have the norm percent error, and these align with each of the bar pairs in figure A. The empty spaces in figure A are null categories, or atoms without any categories. As you can see in figure B, there is very little error. These are very good results. Error remains roughly around 1%. There's some spikes in error, but the average remains roughly 1%. And here's component 2, component 3, component 4. Here is the training, testing, and null loss for the best performing metaparameter and hyperparameter set. The best set in its artificial neural network was then was trained for 500 epochs. Each epoch we would train for an epoch, then do a testing epoch, and then do 25 null set epochs, and average the null set to get a consistent line. And that was done for each component.